So we have this method for improving an approximate solution to an equation called Newton's method. And geometrically, remember that Newton's method just amounts to, if you have some approximate solution, you just find the tangent line at that spot and then follow the tangent line down to its x-intercept, and that x-intercept becomes your new approximate solution. And then you can just repeat this as many times as you want until you get your desired accuracy. So I think it's interesting to actually see this process play out geometrically. So here's a graph of a function. It's not important what this function is, although the formula for it happens to be right up here. And let's imagine that we want to find this x-intercept here, or get a really accurate approximation for what this x-intercept is. So the first thing we need to do is just pick an initial guess, or an initial approximation for what this x-intercept is. And that approximation doesn't have to be particularly good. So let's say it's about 2. Now it's actually quite far from 2, but the thing about Newton's method is it will rapidly, as long as we're close enough at the beginning, we will rapidly get closer to this x-intercept. So let's see what Newton's method does with this. So here's the first step of Newton's method. So first from this, our initial guess for our solution, we go to the corresponding point on the graph. Then we find the tangent line there and follow it down to its x-intercept, and that gives us our next approximate solution. And you can see that it's quite a bit closer to the actual x-intercept we're after than b1, which is what we started with. And then we just repeat. So starting with this x value b2, we go to the corresponding point on the graph down here. So things are getting a little cluttered because of all of the labels, but the corresponding point is right here. And then we follow the tangent line down to its x-intercept. You can see after just 2 rounds of Newton's method, we've gone from pretty far from the x-intercept to quite close to the x-intercept. So if we do one more, go to the corresponding point down on the graph, and then follow the tangent line along. Now we're so close that we actually can't even tell the difference between our approximation and the actual x-intercept. But if we zoom in, we have to zoom in quite a ways before you can see that there is a difference between our new best approximation b4 and the actual x-intercept right there. But if we keep zooming in, we can do this again. So go from b4 down to the corresponding point on the graph down here, follow the tangent line, and now we get a new best approximation that really looks extremely close. We can keep zooming in, right? In general, Newton's method will never give you an exact value for the x-intercept, but you can see that after just a few rounds of Newton's method, so we've done 5, I think, 4 or 5, we're getting really, really close, right? We're off by, if you look at these decimal values, we're off by no more than 200 thousandths, I think. So pretty good. And if we do one more, again, things are looking really, really good. And now our approximate x value is, we're going to have to zoom in for a while before we can even tell that we don't have an exact value. So Newton's method, it's not a trivial amount of computation, but it's not that much computation, and you don't have to repeat this process too many times before your approximations get extremely close to the actual value of the x-intercept. And that's really, really useful because there are lots of ways of approximating solutions to equations or finding approximate x-intercepts, but many of them don't actually zero in on the actual value that quickly. But Newton's method does. It zeroes in on the value very, very quickly. Let's try this trick to find a different x-intercept for this particular function. If we want to find this one that's over here, it looks like it's maybe about a half. So remember, all you need to do is start close enough to the x-intercept that you want, and then Newton's method should work. So what I mean by close enough, I'm going to have to leave a little bit vague, But this point hopefully will be close enough. If we start here and then do Newton's method, so we start from B1, we drop down to the graph, and then we follow the tangent line to its x-intercept, and then repeat. Drop down to the graph and follow the line to the x-intercept, and repeat. Again, we're rapidly getting very, very close to this x-intercept. And this works as long as we're near to any x-intercept. If we wanted to find this one over here, start with this approximation at B1 and then go to the graph, follow the tangent line. Go to the graph, follow the tangent line, and so on. And again, we rapidly get close to the x-intercept we were looking for. Now, your initial approximation does need to be close enough to the x-intercept that you're looking for. So let's imagine that we were trying to get a good approximation for this x-intercept that is at about a half. Is this close enough? Well, let's do a couple rounds of Newton's method and check. So go to the graph, follow the tangent line. Well, you can see that this first round of Newton's method, it doesn't actually get us closer to the x-intercept we were looking for. It actually gets us pretty far from it. And then if we keep doing Newton's method, instead of zeroing in on the x-intercept at a half, we're zeroing in on this x-intercept that's close to -2. So Newton's method, right, it doesn't always give you what you want if you aren't paying attention, right? So you do have to start close enough to the x-intercept that you want in order to zero in on that x-intercept. If you start too far away from the x-intercept you're looking for, you might fly off to some other x-intercept. It's a little bit strange that even though our initial guess, B1 here, looks like, since it's between these two x-intercepts at a half and, I don't know, 1 1/4, you might think, well, Newton's method is going to go to one of those two. But in fact, it doesn't. It flies all the way over here to almost x equals -2. So for Newton's method to work, you do have to get reasonably close to the x-intercept that you're looking for. Right? As long as we're just a little bit closer to this x-intercept at 1/2, then Newton's method will get us close to that x-intercept. So that is something that you have to be careful about with Newton's method. You don't have to get super close to the x-intercept you're looking for, but you do have to be reasonably close.